Hello, hello. So, next up in the mixed model series, we're going to look at this regularization. Can it help us? Can it hurt us? And what we're going to focus on in this video is testing group differences, where you can think of it as having a patient group and a control group, where in the worst case scenario, your patient group is smaller and your patients are more likely to have missing data than your controls. So if you think about this regularization, is that going to shrink all the patients' estimates towards the mean? What's happening? So the setup's a little bit different from last time. Again, the videos probably work best if you watch the whole series, especially if you're new to mixed models. So I'll put a link up here to the playlist for all the videos. You can work your way through them. So I'm focusing on, in this case, also reaction time measured at multiple times for each subject. But now I'm going to break my subjects up into two groups, and we're going to look at group differences. And the idea is some of our subjects are going to have more data than others. So there is an R markdown that accompanies this lecture. So there'll be a link below. I am putting these together into like a book, more of a book format that I will put on GitHub, just in the process of figuring out how to put these all together. But stay tuned for that. Hopefully I'll be able to update the description box with that link as well, but it might take a week or so from when this video goes up. But anyway, that markdown has all the code and results that we're going to go over. And I actually think if you stopped for a little bit and looked over that first and then watched this, you might get the most out of this. Either way, it's up to you. So again, how are analyses of group differences impacted by this regularization? So mixed models have built into them regularization, and the way we viewed that previously was to look at the conditional mode estimates, otherwise known as, sometimes they're referred to as BLUPs. In reality, the BLUP is just a prediction that goes in to the full estimation of within subject estimates. But anyway, these conditional modes can help you visualize the regularization, but it's not always 100% representative of what the mixed model is doing. That's really what I want to get across today. This illustration is from last time. The uneasy subjects are subjects with less data. The sort of ghosted faces indicate within subject means of, say, reaction time or some measure. The green line is the overall group mean, and you can see the subjects with less data, they're within the mixed model, their contributions get weighted toward or dragged toward the group mean, whereas the subjects with more data get regularized less. So regularization generally is a good idea, sort of giving more credit to subjects with more data and trying to stabilize estimates from subjects with less data. But again, for my friend, when I was explaining this to her, she's like, my data almost look just like you've laid them out here, but these are all my patients and these are all my controls. If my patients are being sucked towards this mean and my controls aren't as much, is that going to hide group differences? So the goal here is to make it more clear what that regularization actually looks like and to avoid a pitfall that I've seen. It's not super common, but I have for sure seen people use conditional modes in analyses, and you should not do that. Okay, so again, let's gain some more intuition about how conditional modes are not a perfect way of understanding the regularization from within the mixed model. And you should not use these, you should not extract these estimates and then use them in other analyses. It's a bit dangerous. So we're going to look at 4 different modeling approaches using a plain old mixed model, modeling group with a random intercept, repeated across subjects. The 2-stage summary statistics approach, or 2SSS, where I use ordinary least squares at both levels. OLS just means linear regression. In this case, it would be a mean within each subject and taking those within subject means and running a 2-sample t-test. Again, you can do that, both of those steps within linear regression. Then I have 2 what I call pseudo 2-stage summary statistics approaches, where in the first level, instead of using OLS, we're going to extract conditional modes from mixed models. The first mixed model doesn't model group. So this is what I've seen most frequently, is folks will run this model and extract the conditional modes and then put those into the 2-sample t-test. The last approach is doing the same thing, but the conditional modes are extracted from a mixed model that does have group modeled. So we'll see the big difference between these two approaches is what the regularization is toward. In this model, it gets regularized towards the group mean because that's, or not group mean, the overall mean because that's all that's modeled. Whereas this model, the regularization is done differently for each group because that group's mean is used instead of the overall mean. Makes a huge difference. Okay, I'm going to simulate 4 different study designs. So basically, for each of these, I'm going to generate 1,000 data sets and analyze them. The first one is going to have 25 subjects in each group, where all subjects have 30 observations, so everything is balanced. Then 25 subjects in each group, so I have balanced patients in control group, but 5 of my patients only have 5 observations, while everybody else has 30. Next, now we're going to work into imbalanced groups, so 10 patients, 40 controls, but everybody has balanced data. Then 10 patients, 40 controls, 5 of my patients only have 5 observations, everybody else has 30 observations. So how to investigate and compare? I always view model performance first through the lens of type 1 error rate and then power. If type 1 error is not preserved, you cannot assess power, because if you only look at power, and I've seen papers that have done this, heck, I've probably done it too, but it's wrong. A method can have very high power, but if the type 1 errors aren't preserved, it's pretty meaningless because you don't know if it is truly power or just a bunch of false positives in practice. So here's the function that makes the data. It's very similar to before, but now I have allowance for different group means. My group 1 mean will be set to the same value as the group 2 mean when I look at type 1 error, because that would be the null. And then I can change the within subject variance, between subject variance, the amount of data each subject has. So this is a vector, and then a group vector, and so on and so forth. I'll let you read through this on your own. Very similar to the other simulation code that I've gone through. Then I have a separate function for running the simulation. So I have to generate 1,000 data sets at least. So that's what nsim is. Otherwise, these are just the variables that get fed into that function I just showed you. Randord, nsub, I didn't actually use that here, but this nwin sub vector has the number of observations within each subject, and by default that's ordered to match up with the group vector. So if I wanted to randomly choose who has only 5 observations, I can just shuffle this vector. So this randord nsub will randomly shuffle that for each simulated data set. So that would be if I just wanted 5 subjects, regardless of patient or control group, to have less data. So I don't have any simulations I'm presenting with that setting here, but feel free to run it on your own. This code does take some time to run, obviously, with 1,000 simulations. So if you have a cat like I do, don't leave your laptop unattended, because they always lay on your laptop when it's running simulations because it gets so nice and toasty. Or my cat likes to sit on the lid and shut the laptop, which is great. Anyway, here's more of the code. This is basically, I'm just showing you this to show you the different models that are used. So here's that mixed model. So this is, spoiler alert, the best way to go. So I just have the group variable and then a random intercept. That's the first one. Then we have the 2-stage summary statistics approach using ordinary least squares at each step. This is stage 1. It's actually a trick that you can use to get within subject means really quickly. I could have used functions in tidyverse as well to get within subject means, but I don't know, this is one line of code, so I'm sure the tidyverse one is too. But all this is, again, is extracting the mean for each subject. And then here, I'm just running a 2-sample t-test, but I'm using a linear regression model to do it. Then I have the pseudo 2-stage summary statistics approaches. This first one is the one using conditional modes from the model that includes group. So that's this model right here that I already ran. So this is pretty stupid, right? Because this model already had the p-value I needed for comparing the groups. But instead, I've run this model. Now I'm going to pull out the conditional modes for each subject, and then I'm going to run a group comparison on those. You might think, Jeanette, that's ridiculous. But I've seen it done before, so that's why I'm assessing it. Last but not least, this is probably the more common way to extract conditional modes, is just have a model with an intercept in it and extract the conditional mode for each subject and run a 2-sample t-test of those. So just spoiler, the bias here is going to be towards the mean of each group. The bias here is going to be toward the overall mean. That's problematic. Okay. Here are the measures we're going to focus on. We could just look at p-values, but then you don't know why the type 1 error was preserved or not preserved or what's driving power. So what we're going to do is we're going to first look at the numerator of our statistic, which is just the mean. So we're going to look at the means within each group as well as the group difference. And then we're going to look at the standard errors. If standard errors are too small or too big, that's bad. In this case, we're actually, I guess I'm spoiling the surprise, but they're going to end up being too small. Okay, starting with the type 1 error investigation, there's a lot going on here. I'm going to unpack it. So we're looking at the group difference. So I'm going to look at each mean separately, group 1 and group 2, as well as the difference. So this last one would represent the numerator of our test statistic. The different colored boxes, those are the different models we're using. So LMER, the 2-stage summary statistics approach using OLS at each stage, the pseudo 2-stage summary statistics approaches. The green one is where group was not in the model, and the yellow is when group was in the model. And then we have each group clustering of boxes is for different data scenarios. So this is balanced groups, 25 patients, 25 controls. Nobody had a low sample size, and that's the same for all of these. Then we have, again, balanced 25 patients, 25 controls, but 5 in group 1, 5 in the patient group had only 5 observations, while everybody else had 30. Now we have imbalanced group, 10 patients, 40 controls. Everybody has 30 observations. 10 patients, 40 controls, but 5 of the patients only had 5 observations. Okie dokie. So generally, if we first just go through these really quickly, the true group mean is the solid line. It's 10 in both cases because these are null data. And you can see that generally the boxes are all nicely centered about 10. And then the group difference is centered about 0 for all the cases. So generally the estimate of the difference seems about right. But if you look carefully and you look at the distribution spread, you'll see that in this case, this is the pseudo 2-stage summary statistics approach where there was no group in the model. You can see these estimates tend to be closer to 0. So there's some sort of bias happening here, but it's not happening using the pseudo 2-stage summary statistics approach when group is modeled. And that's because our patients are being biased towards 0 because they have less data. I'm sorry, they're being biased toward 10 because they have less data. So their estimates are less variable over simulations. It doesn't happen for this group because everybody has, this is the group 2 mean and everybody has 30 observations. And then in the group difference, you can see that spread is a little bit lower across the board. It's just more emphasized in the scenarios where the patient group is smaller and there's more missing data in the patient group. So that's interesting. So the numerator of our t-statistic is going to likely be too small for the pseudo 2-stage summary statistics approach where no group was in the model. And that's because that shrinkage is toward 10. So what does that look like in terms of standard errors? So here we just have one set of standard errors. This is for the group difference. And we can see the pseudo approaches have underestimated standard errors. So again, this is the distribution of the standard errors across the 1,000 simulations. And spoiler, smaller doesn't necessarily mean bad, but in this case it does. There's also this case here, the 2-stage summary statistics approach. The standard error is too small there. Otherwise, the standard errors roughly match between LMER and the 2-stage summary statistics approach. So In this case, the smaller ones are actually not accurate. If you underestimate standard error, that can inflate your type 1 error rate, and that's exactly what we see here. So interestingly, the green standard errors, those were underestimated, but the type 1 error is preserved. So the goal here, and I'll explain why in a second, let me just tell you the goal is to be in between these dotted lines because that's within the 95% confidence interval of 0.05. So everything's going okay except for most of the ones that had standard errors that were too low. But why did these green bars land within the good range when their standard errors were too small? Well, it's because the standard error, which is the denominator of the t-statistic, was too small, but so was the numerator. So remember, these, even though it's not very dramatic, generally the values were shrunk towards 0, so the numerator is biased towards 0, and the denominator is too small, and too small cancels out too small, and you end up with preserved type 1 error. So we'll see if that's still okay. So far, only these are out of the game. We cannot consider these for power, so I'm going to ghost out the bars when I look at power. I almost asked if there are any questions, but obviously you could say them, but I can't hear them and answer. If you have any questions, definitely post them in the Facebook group or down below. So moving on to power. So now I change the group means, otherwise everything's the same. I have a mean, the true group mean here is around 12, and here it's 10. So there is a group difference to be detected. And generally things look okay, except for these green boxes again, because you can see the bias in this case is toward the overall mean because I didn't model group. So yeah, you can see these green boxes are being dragged down, especially in this case, because again, the patient group is small and 5 patients have less data, so the regularization effect is stronger. But that regularization effect isn't hurting the actual proper mixed model. It's only when we start pulling out these conditional modes. The conditional modes look okay in the mixed model where we had group modeled, but again, this one's been axed already because the type 1 error was not preserved because the standard error was too small. Okay, group 2 is generally okay-ish. Not too many problems you can see there, but in the differences, you can see the differences are biased for the pseudo two-stage summary statistics approach where group was not modeled. So things are not looking good there. There's still the other ones that are still in the game are the mixed model and the two-stage summary statistics using OLS, but just these. This one we know doesn't work. Okay, standard error is very similar to before. We have the same ones with underestimates in the standard error. And here's how power comes out. So again, I've ghosted out the power bars for the methods for which the type 1 error is not preserved because it's too misleading to look at power. I mean, the power looks really high right here, right? But the type 1 error was also close to 9 or 10%, which is not acceptable. But otherwise, we can see the type 1 error, or I'm sorry, the power is very similar across the other approaches. Here, we have a big loss in power, though, between the mixed model and the two-stage summary statistics approach using the conditional mode without group in the model. And that loss in power is, again, I'm going to flip back because of this bias that we're seeing here. We're not seeing the difference. It's biased towards 0. So it's hiding the effect. So because of that, I wouldn't ever recommend extracting conditional modes and using them in analyses. There are other scenarios I'm going to show you where it's even worse, but so far outlook not good. LMER is always the winner, and in some cases OLS matches almost exactly to mixed models. When you're in trouble using the two-stage summary statistics approach is when you have imbalanced groups with imbalanced data. So my rule of thumb, as I said before, I've been stuck in a jam where I have to use the two-stage summary statistics approach because there isn't a way to answer my question using a mixed model. And so since my data were balanced within each subject, I felt very confident that what I was doing was okay. So again, I talked about this example before. It was looking at the relationship between a variable A and B in a mixed model, and then looking at the relationship between A and C. And the folks I was helping wanted to show that that relationship was stronger for A and B than A and C. Now you can't test that within a mixed model. Putting B and C in the model together doesn't answer that question. What you would use if you didn't have repeated measures is a test to compare to dependent correlations. So there isn't a simple analogous test using mixed models. So what I did was I did within subject averages, and I tested, used that dependent correlation. But since data were balanced, I felt confident doing that. All right, winner, winner, chicken dinner, LMER, not a surprise. So use a mixed model whenever you can. The two-stage summary statistics approach, it doesn't work as well under heteroscedasticity. If you want a little intuition as to why, this is exactly why Welch's two-sample t-test exists. That wouldn't help here necessarily because it's not tapping into that same problem, but it's because the variance of one group is different from the other, and it's just ignored when we use the two-stage summary statistics approach. So the standard error can be underestimated, and that's very bad because that inflates our type 1 error. Yes, so fMRI people, you're doing this all the time. So keep that in mind depending on the software you're using. The pseudo two-stage summary statistics models, generally the standard errors are going to be so small. We're using these really noisy predicted values and completely ignoring the fact about how noisy they actually are. We're just pretending they're true values of within subject means. And depending on your model, the conditional modes are going to be biased in a way that can hurt you in your modeling. So even in the cases where type 1 error was okay, the power was lower. So I really cannot recommend it. And when the conditional modes that had group in the model, the type 1 error was not controlled. So that fixed the mean bias, but then the standard errors were not correct. So the takeaway, again, just use a mixed model when you can. Conditional mode-based estimates have this unaccounted variance. So it's fine, sometimes you plot them in papers just to show what's going on with your subjects, but inference cannot be trusted, underestimates the standard errors, and just be careful about using them. So for next time and later on, I'm going to talk more about the regularization of within subject slope estimates, so that's coming up later, but I'm also going to look at between subject slopes in the very, very next video. So instead of group differences, what if I was looking across age and my oldest subjects were missing data compared to the younger subjects? Also, there's this thing in the Bates book that was really misleading for me, and I can't wait to clarify that because I wonder if it's confused other people. And again, look, as I said, I'm going to look at a continuous between subject variable age. If you have questions, please post them to the Mumford Braidstaff Facebook group or in the comments below, and I will get to you as soon as I can. All right, have a great day. Thanks for watching.